So today we are going to be graphing rationals. When we're graphing rationals right now, what we're really going to be doing is we're going to be looking at our key features. I don't necessarily need you to graph these by hand. What I need you to be able to do is to recognize these key features that I'm going to talk about today. If you can recognize the key features, you're going to be able to recognize the graph, and that's our goal. We just want to know what this behavior is and why it happens, and then we see what it looks like on a graph. Okay, so the key features that we're going to be looking at when we're graphing our rationals are vertical asymptotes, which are vertical lines that our graph is going to come in and get really close to, but it's not going to touch our vertical asymptotes. Okay, horizontal asymptotes are horizontal lines that our graph, again, is going to come in and approach. Sometimes it can cross a horizontal asymptote because there's no mathematical issue with that, but a lot of the times it won't cross, but sometimes it can. Vertical asymptotes will never cross. Horizontals, it's totally fine. We're going to find X-intercepts of our graph, Y-intercept, and if there's a hole in the graph. A hole in the graph is kind of hard to think about and visualize, but it's literally just like if you had a graph, there's just a teeny tiny little gap. So we'll talk about it. If you have questions, let me know. So I've got an example over here. It's written in factored form. So this right here is factored form. And this one right here is standard form. Both of these are going to give me information I need to find these key features. So I'm just going to breeze through this one, talk about where we find them, show you an example, and then I'll come back with some more examples so you can see it a little bit later. So first thing we're going to look at is vertical asymptotes. Vertical asymptotes come in after it's been simplified, and we'll see that for specific reasons. Actually, yeah, once it's fully simplified. So I'm going to put that note here. You're looking at the fully simplified function, and our vertical asymptotes happen when the denominator equals 0. So if the denominator equals 0, that's where we're going to see a vertical asymptote. So here, if I'm going to simplify it, my x plus 2's cancel, and so I'm left with x minus 3 over x minus 1. So I'm looking at my denominator here to find my vertical asymptote, where that equals 0. So x minus 1 equals 0. I'm going to have a vertical asymptote where x equals 1. Okay, and I'll show that on a graph here in a second, but right now we're just figuring out where they are. A horizontal asymptote, okay, what we're going to look at here is we're going to look at standard form. And what we're using is called the end behavior model. What we're looking at is the highest exponents and comparing them. The highest exponents are going to tell me which horizontal asymptote or how my horizontal asymptote behaves. So I'm going to look using standard form, which I wrote over here. See? Standard form. I'm looking at the highest exponents. So here I have an x squared over an x squared. We have an x squared in the numerator, an x squared in the denominator. They are equal exponents, right? So for my end behavior model, when they are equal, we just look at the ratio or the proportion of our highest exponents. For example, this is x squared over x squared, which is going to reduce to 1. That tells me I'm going to have a horizontal asymptote at y equals 1. I'm going to write that here. Okay, if this happened to have said 3x squared over x squared, that's going to simplify down to 3. So then I'd have a horizontal asymptote at 3. So we just look at the ratio there. So I'll put that here. When they're equal, look at the ratio. There are two other options here, so we're going to go through those real quickly. They don't apply to this problem. But I'm going to say if it is top-heavy, meaning the higher exponent is in the numerator. So an example, x squared over x. Top-heavy because the highest exponent's in the numerator. When it's top-heavy, we do not have a horizontal asymptote. We have what is called an oblique asymptote. So instead of being horizontal like this, it's slanted in some way. So we don't have to deal with those very often, but we still want to be able to identify when they don't happen. And then our last example would be if our equation is bottom heavy. So an example of that would be if we had x over x squared. If we have x over x squared, meaning it's bottom heavy, our horizontal asymptote is always 0. So we're either going to look at the ratio when it's equal. It doesn't exist if it's top heavy, and if it's bottom heavy, it's equal to 0. Okay, horizontal asymptotes. My x-intercepts. This comes from my fully simplified equation. So we've already fully simplified, right? That's this guy. Our x-intercepts come when the numerator equals 0. So when the numerator equals 0, our entire rational function equals 0. X-intercepts happen when y is 0. That's our x-axis. So I want to know when the numerator equals 0 to find my x-intercept here. So I'm going to take x minus 3, set it equal to 0, and I'm going to have an x-intercept when x equals 3. So I'm going to write that as a point. The x-intercept is 3, 0. Okay, cool. The y-intercept. In the y-intercept, what I'm going to do is I'm going to plug 0 in for x. Plug 0 in for x. Now, x equals 0 for the y-intercept. So I'm just plugging in 0 for x, and that's going to tell me my y-intercept. So if I come over here, 0, 0, that's negative 6. 0, 0, that's negative 2. So my y-intercept is coming from negative 6 over negative 2, which is 3. So when y equals 3, I'm going to have a y-intercept. So that's the point 0, 3. Okay, and then our last key feature is if there's a hole in the graph. Some computer systems can't show a hole in the graph, but I'm going to show you what it's going to look like for us. So a hole happens anytime we're able to simplify or reduce our function. So if I can simplify or reduce my function, I'm going to have a hole in the graph. So here, notice that I was able to cross out my x plus 2 divided by x plus 2. Though simplified to 1, I removed it from the function, is why it's a hole. I'm going to remove it from the graph. So the hole in the graph happens where that equals 0. The reason it becomes a hole is because if I plug in negative 2, I'm still dividing by 0, which could create a vertical asymptote. But because I removed it, it's now a hole instead of a vertical asymptote. So I have a hole where x equals negative 2. So I'm going to quick show you a sketch of this rational function, and then we'll go through another example on another video here. So my vertical asymptote is at x equals 1. The vertical asymptote doesn't really exist, but we're going to see our graph approach it. And then I have a horizontal at y equals 1. I have an x-intercept at 3, 0. And I have a y-intercept at 0, 3. And then once it's graphed, I'll come back and show you the hole. So because I have an x-intercept here, this piece of my graph is going to look like this. And then my second piece is going to look something like this. And the last thing I need to come in is show the hole. Where x equals negative 2, that's where my graph is. There's a hole right there, meaning that y value doesn't exist because I can't plug in negative 2 into my function. Okay, if you want, jump on Desmos.com, type in this equation, and check to see if I graphed that properly. Okay, I can't show it to you here, unfortunately. I just have a whiteboard, but trust me, this is how it works. I'll come back with another video.